We know that every linear transformation from Rn to Rm has a matrix. And we even know how to find that matrix in a pretty straightforward way if we have a formula for the linear transformation. But one thing that we can't do right now is if we start with a linear transformation that's only defined on some subspace of Rn, we don't have any way of coming up with a matrix for it. So, what can we do? If we have some two-dimensional space sitting inside of R3, this is supposed to be an R, and it maps to some, I don't know, some other subspace in some other Euclidean dimension, right? Because there's this, right, we only have a matrix if this linear transformation is defined on all of R3. If it's only defined on this subspace, then there's no matrix, right? At least no matrix that has three columns, because the linear transformation isn't defined in this third direction. But if we want to come up with a matrix, clearly we should want to come up with a matrix because using a matrix is sort of how we do calculations. So we should want to come up with a matrix, but to be able to attach numbers to things, what is it about R3 that lets us write a matrix? Well, the feature of R3 that lets us write a matrix for a linear transformation is the fact that it comes with this handy basis built in, right? We are so familiar with this basis for R3 that we don't even really think about the fact that this is sort of a special, having a built-in basis is a special feature. So maybe for this subspace here, what we should do is write down a basis for it. We know from experience that one way of looking at a basis is that it's sort of acting like a coordinate system, right? If you have a basis, then every vector in that subspace or in the span of your basis vectors you can write it uniquely as a combination of the two basis vectors. And that combination, so if this blue one is v here, and maybe the red ones are a basis vector v1, v2. So you can write any vector in the span of your basis as a linear combination of the basis vectors. If there are only two of them, then it would look like this. And you can see if you sort of squint to just right, this looks as if we have the vector a1, a2, right? And a1 and a2, those are scalars, so they're acting like coordinates. And the basis is just sort of what gives those coordinates meaning in the context of R3. So maybe what we should do is make this precise, sort of come up with a linear transformation that takes this vector space and sends it to these coordinates, right? So if we have some subspace with a basis, say, v1 up through vk, so, this subspace might be in Rn, in which case we can't assume that the basis for the subspace has n vectors. It might not fill out all of Rn, so k is going to be smaller than n in general, or less than or equal to n anyway. So suppose we have a subspace with a basis. Then for any vector in our subspace, we can write this vector as a linear combination of our basis vectors. Sorry, these should be pluses here. So write this vector as a linear combination of our basis vectors. And the key thing here is that this representation is unique. So I'll say write v equals this sum uniquely. And what I mean by that is there's only one way to do this, right? There's only one way to choose the coefficients that makes the right-hand side equal to the left-hand side. And this is because we have a basis, right? We've seen that having this unique sort of representation is a feature of having a basis. Okay, so then we can define a linear transformation from V to RK by, we're using these as coordinates, so let's call this the coordinate transformation, C, and it depends on the basis that we started with. So let's decorate this C with a little B for basis, right? And we can call this set B. And so so this is coordinate transform for the basis B, and we'll define it on this vector just by saying the result over in RK is just the coefficients, A1 through AK. All right. Now, one thing that isn't obvious is that this actually is a linear transformation, but it's not too tricky to see that. I mean, first of all, let's just evaluate. Let's evaluate this on the basis vectors, the v1 through vk. Well, v1, right, as a linear combination of the basis vectors, v1 is 1 times v1 plus 0 times v2 plus, all the rest of them are zeros. And so if we just pick the coefficients, we get 1 and then nothing but zeros. Right, so that's what this does to v1. This coordinate transformation to v2, well, you can see the same thing is going to happen, except the 1 is going to show up on the v2 instead of in front of v1, and zeros elsewhere, so it's going to have a 0 there, a 1 in the second entry, and then zeros elsewhere, and so on. Right, this coordinate transformation is going to take vk to the vector that has zeros everywhere except in the kth entry where it has a 1. Right? And you can check that this satisfies I'll let you check that this satisfies the property for linear transformations. In fact, it does. It's not hard to prove. That's a good exercise that you should do. So this linear transformation, C, the coordinate transformation, is going to be our way of attaching numbers to vectors in a subspace when maybe we don't know that much about the subspace, or it's somehow inconvenient to deal with the vectors in the subspace directly. So instead of dealing with these vectors directly, instead we can deal with their coordinates. So that's the idea with this coordinate transformation. It's just defined by our coordinate transformation applied to any of the v's is just the vector that has a 1 in the corresponding entry. And this is the linear transformation that just picks the coordinates off of your linear combination. Okay, so just to get some feeling for how this coordinate idea works, let's say we have a vector space V that's given by the span of these two vectors. These two vectors are linearly independent, so in fact they serve as a basis for this subspace V. And let's say that v little v is a vector in capital V that has 2 and minus 7 for its coordinates. Then let's write v as, this should say as, an element of R3. So right, this basis defines a coordinate mapping, and we know the output of this coordinates, so we know the coordinates of little v relative to this basis. But remember what that tells us, right? These coordinates, they're really the coefficients for the basis. So our vector v is the coefficient in the first position times the basis in the basis vector in the first position, 4, 1, minus 1, plus the coefficient in the second position times the basis vector in the second position, 3, minus 2, 1. So now it's just some arithmetic. So let's see, 8 minus 21. So that's going to give me, I should have chosen easier numbers, negative 13, and then 2 plus 14 is 16, and then minus 2 minus 7 is minus 9. Okay. Right, so the general idea here is if you have, so this is in general, not for this particular example, but the general idea here is if you have the coordinates for a vector, then you can sort of reconstruct the vector itself because you just use those coordinates as coefficients on your basis, right, like this, which is essentially what we did here. But this is how it works in general. You can see that if we have coordinates, so going back to this particular example, if we had any coordinates, right, one way to rephrase this here is, well, this is just the matrix whose columns are the basis vectors times the coordinates that we started with, and that produces V, right? So really, I mean, it's sort of amusing how no matter what different concepts you come up with in linear algebra, everything comes down to writing down some sort of vector equation like this. Okay, so if you have a basis for your subspace and you have coordinates, you can find the vector that produced those coordinates just by doing this matrix product, right? Take your basis, dump them all into a matrix as columns, and do your matrix multiplication with the coordinates on the right. Something to notice about this is that the order of this basis matters, right? If we put these columns in the other order, the coordinates would also be in the other order. So you have to be careful. When we write a basis like this and when we talk about coordinates, the order of the basis matters, even though we're using these curly braces. Usually in math, curly braces indicate a set, and usually when you're talking about sets, the order of the elements doesn't matter. It only matters which ones are in there, not what order you list them in. But this is one situation where the order does actually matter. So, heads up, be careful about that. All right, so here we had coordinates and we reconstructed the original vector. We could go the other way. We could have a vector and find its coordinates. So to do that, let's do that with this vector. So we have the vector 3, minus 4 in R2. Let's find the coordinates of this with respect to the standard basis, and then afterwards we'll look at a different basis. So we're going to find the coordinates with respect to B1 of 3 minus 4. Okay. So there are two ways to think about doing this. Maybe the first way is, actually they're both this way, but stated slightly differently. So to find the coordinates, we just need to express this vector in terms of this basis, right? There will be some coefficient times E1 plus some coefficient times E2, and then the coordinates will be whatever these coefficients are, right, here and here. For the standard basis, the standard basis is in R2, since it's just 1, 0, and 0, 1 in that order, the coefficients are really the same as the entries. So a 3 here and a 4 there, minus 4 there, right? So the coordinate vector will just have these entries, so 3 and minus 4. Notice that in R2 with the standard basis, the coordinates are the same thing as the original vector, right? So really, this whole time when we've been talking about vectors with entries, these are really the coordinates with respect to a standard basis. All right, so now let's take the same vector, but let's write it let's write its coordinates in terms of this basis. So different basis, so its coordinates are probably going to be different. They will be different. So the coordinates with respect to this new basis of 3 minus 4, right, to compute this, what we would do is write 3 minus 4 as some linear combination of these basis vectors, 1, 1, and 1 minus 1. Right? And then the coordinates will be just the coefficients, a1 and a2. But, you know, this right here, this is the same thing as 1, 1, 1 minus 1 times a1, a2. And this is supposed to be equal to this vector here. So that's 3 minus 4. So you can see all we need to do is solve this linear system, and we'll have the coordinates of this vector 3 comma minus 4 relative to this basis. So, you know, how do you solve this sort of system? You augment and then reduce. So we can subtract the first row from the second row. We get 1, 1, 3, 0, minus 2, minus 7, I guess. And then now we can maybe divide second row by minus 2, so 0, 1, 7 halves, and then subtract the second row from the first row. So I'm sorry, this should be a 1 right here, not a 2. Okay, then we get 1, 0, and then 3 minus 7 halves is 1 half, right? 0, 1, 7 halves. Okay, so we solved this equation. That means this is a1, a2. So the coordinates with respect to this second basis of the vector 3 minus 4, the coordinates are 1 half and 7 halves. All right. Well, so, I mean, you can see this particular example was a very nice case because we have a basis not just for some, so both of these, right, this basis is an R2. This is sort of a special case because this basis isn't for a subspace of R2, it's actually for all of R2. And so in this case, right, what we ultimately ended up doing was we took this basis for R2, we took the vector that we wanted, put it on the right-hand side, right, and then just put the basis as columns into this matrix, and then solve this equation, right? But that whole process is going to work essentially the same way if we have a basis for any Euclidean space, Rn, right? So let's look at that special case. So suppose we have a basis for Rn, so the basis is going to be V1 up through Vn, then the coordinate transform has a matrix. What is that matrix? So in this case, we need to remember that these V's are in Rn, right? Each one of these is Rn in Rn. Okay, so what we noticed before was if we take a matrix, so actually let me write it this way. So if we take the coordinates for any vector here, right, we get some result like this. What we noticed in the last slide was that this means this is the same thing as saying if you take all of the basis vectors and put them into the columns of a matrix, which makes sense because remember they're actual Euclidean vectors in Rn. If you multiply by the coordinate, the vector of coordinates, what you get is the original vector, right? So this looks like a linear transformation. Is this the coordinate linear transformation? Well, no, because the coordinate linear transformation has v on the left and the coordinates on the right, but this one is the other way, right? It has the coordinates on the left and the vector on the right. In other words, all we need to do is solve this equation for the coordinates. But to solve this equation, all we need to do is find the inverse for this matrix. So if we multiply both sides by the inverse, what we get is, multiply both sides on the left by the inverse of this matrix. We get, on the left, the matrix, the inverse times this matrix is the identity, so it's gone. So we are just left with the coordinates. On the right, we get, we multiplied on the left by the inverse of this matrix times v. Okay, so on the one hand, sending v to its coordinates, that is the coordinate transformation. But on the other hand, sending v to its coordinates, you multiply by this matrix, right? So in this special case, where we have a basis for Rn, the coordinate transformation is multiplication by the inverse of this matrix that has just the basis vectors as its columns. You might recognize this basis. We actually, when we were finding the matrix a long time ago, when we were finding a matrix for a certain linear transformation, we actually did exactly this trick. So this is something that we've seen before, but right now we're sort of rephrasing it in a different context. There's one other interesting property about this coordinate transformation, right? It is a linear transformation. In general, it goes from whatever vector space you're starting with to some Euclidean space, right? And it turns out that this linear transformation is actually an isomorphism. So suppose we have some subspace of Rn, and it has a basis of v1 through vk. So this in particular, this means that the dimension of v is going to be k, because if we have a basis with k vectors in it, a basis for v, capital V, then this coordinate linear transformation goes from v to Rk, and it has to be Rk because, right, any linear combination of these basis vectors, since there are k basis vectors, there are also going to be k coefficients, right? So the coordinate transform applied to this vector just gives us a1 through ak. All right, well, look, these two, so we're trying to show that this is an isomorphism. Well, these two spaces both have the same dimension. They're both dimension k. Rk is obviously dimension k, and v is dimension k because it has a basis with k vectors in it. So we know these two spaces have the same dimension. When we know two spaces have the same dimension, we have a lot of different choices for how to show that it's this transform is an isomorphism. We could show that it's one-to-one, or we could show that it's onto. But with this formula, it's obvious that it's onto. We could make any list of coordinates appear here just by putting in the appropriate or the corresponding coefficients up here. So this C sub b is clearly onto for this reason. And when you have an onto transformation between spaces of equal dimension, that means that it's an isomorphism. Okay, so these coordinate transformations always give you an isomorphism. Different choices of basis will give you a different isomorphism, but there's always, every choice of basis does give you some isomorphism. And if all you're looking for is sort of a concrete Euclidean space that looks like your subspace, right? Any choice of basis will give you this nice correspondence that lets you view your subspace as a Euclidean space.